Good morning, everyone. I give you a few minutes to arrive, but thought I'd start the stream ahead of time. And I should have a little warm-up survey on Slido. Today we will talk about all sorts of data structures and elementary algorithms on those. And I want to make this a little bit dependent. How fast I go over some of the topics will depend a little bit on how much of this you already know. So that's why I want to collect this data a little bit. Yeah, so I would love to see high turnout rates on this. Even if you haven't seen any of these, just vote none of these. That's also useful information for me. While we're waiting, I wanted to make a comment about the class tests. They're not started yet. You might have seen the question on CampusWire. The tutorials are different from the class tests in that there's no hand-in for tutorial problems. You just have these for practice and for exercising. And you will go over solutions with Ben, but there's no requirement for you to hand those in. For the class tests, those will be quizzes on Canvas, and I will announce them in due time. The timing will roughly be, we first cover something in class, in lecture, then there will be a tutorial where you practice it, and then at the end of the cycle, if you like, for some of the topics, not all of them, we'll do a little class test, just to give you some more impetus on really understanding that in depth before we eventually head to the final exam. So the class test will always have these two components. There will be a practice problem that you can just try out and nothing happens. But then there's a second part that you have to do, and it counts when you submit the answer. More on that next week then, when also the first one, by the end of next week, I expect the first one might start, depending on how fast we get through and how the tutorials go. Any other organizational announcements? Let me think. Yeah, people have started forming groups for the videos, the video presentation. That's great, so keep that in mind. You have another week, so no rush with that, but use the tutorials and the space on CampusWire to find a team and start thinking about what articles might be interesting for you to have a look at. Okay, with that, I think it's time to get started. And I first want to show the results of this little survey. You've seen that on the side. So people know what arrays are. That's great. And not so many people know what linked lists are like. So I'll talk a little bit about that. And so people have seen binary search trees, but only a few of you, and none has seen a binary heap. So we'll spend some time on that. I won't have time to cover hash tables in this class, even though it's a very classic and important and useful and great data structure. Maybe that's something for the future to keep in mind, that this might be useful. We will not need it in this class. It's just one of the things, everything on this list except for Fibonacci heaps and skip lists are fairly elementary data structures that are very useful to know. So thanks for participating in this, and let's get going. Welcome to Unit 2 on fundamental data structures. This will be the first unit where we really dive into the computer science topics, and we leave the mathematical preliminaries behind us, finally. It will be a recap unit for all of you who have an undergraduate degree in computer science. You will have seen most of what I present, and I also will go over this at a fairly rough pace. So there's a lot of extra material on the website in particular really well done lecture videos, professionally studio recorded ones. They're not for free, but they're really worthwhile investing time and a little money into them if you want to understand these topics in more detail. For what we need in this class and for your course, everything will be covered in the lecture. But again, if you feel you want to be a full-fledged computer scientist, you won't get around knowing the basics of these data structures. And my lectures today and next week will probably only scratch the surface. If you want to go deeper, you're encouraged to check out the website. But that said, let's see what I can do for you today. We'll talk about the very basic data structures, and I will probably start with a little bit of what linked lists are. Maybe just the term was not what you knew. We'll talk about resizable arrays and as a building block for other data structures. And finally, the two big classic data structures in computer science that build on these very elementary ones, priority queues and binary search trees. First, very basic data structures, stacks and queues that you might have seen, or maybe even the terms are intuitive enough to make out what they mean. But I will use these to also introduce the concept of abstract data types, which is an important conception, an important concept in computer science that people found very useful. So let's look at what that is. The contrast is to be drawn between abstract data types on the one side and concrete data structures on the other side. And if you've learned programming in Java, then it will help you to think about abstract data types as something like the interfaces in Java, where you specify the operations of the methods, but you don't provide any implementation. And data structures are the concrete classes that implement a certain interface. Of course, you can have classes that don't implement any interfaces, but what I really mean is you have an abstract data type on the one side, an interface, and then a class that implements it. This analogy is useful, but it's not a complete and true representation of what abstract data types are. So it's helpful to keep the two separate. Oh, I see. Someone pointed out that the question I asked only allowed one answer, and that's of course nonsense. So let me maybe open that one again. And let's reset the results and just do that exercise again. Thanks for pointing that out. It's a weird interface in Slido. If you don't say limit options, then it's just one. Okay, so we get a different turnout. I'll briefly show the turnout in a minute. The distinction between abstract data types and data structures is fundamental, so I want to cover that part either way. So Java interfaces are what you can think of, but an abstract data type has to have a little bit more than just a method name. It has to list the supported operations, but it should be precise in specifying what exactly should happen. So you want a little bit of a clear description. It can be natural language as usual. If we're doing this for humans, it can also be a little more formal than that. What it does not specify is how to implement the operations, and it also doesn't say how to store data that is associated with a certain data structure. And on the other side, data structures do exactly that. They tell you exactly how the data is represented. They tell you exactly how the operations are implemented. And it has, because of that, the algorithms have concrete cost in time and space. Using the analysis methods from the last unit, you have an idea how to work out these costs. So this is what you can really implement in a program and what you can run. An abstract data type is just a shallow interface where you can't really use this to run a program. You always need an implementation. You can argue why it makes sense to separate the two. I can think of a couple of reasons. From a practical perspective, it's helpful if you can swap out implementations. That's what people in Java do a lot. You can say, I have a list of objects, and then you can specify it's a linked list or an array list. That makes code more reusable, both on the client side that uses a data structure or an abstract data type then, and on the implementation side of a specific abstract data type. You can create linked lists once and use them wherever you need them. It's also helpful because it often allows better abstractions, and I think this is it's underappreciated how much that helps to build programs and to understand a task at hand, a computational problem. And lastly, it's also the way to approach lower bounds. If you can isolate the functionality of a certain task to an abstract data type, you can talk about what are the best possible implementations for this abstract data type. That's something that's hard to do if you always mix your data structure with client code. Okay, with that, let me show the results from the opening poll again. People still know arrays, but half of you know linked lists. That's reassuring. And many of you have seen binary search trees. A quarter or so has seen binary heaps. And okay, good. So I was figuring some of you must have seen the more advanced data structures as well. Good. So as I said, I won't talk about hash tables, and I won't talk about these two, but we'll talk about the rest and do that somewhat briefly. Okay, let me tick off these two. As a last point, I want to mention that despite all these positive aspects of having the separation between abstract data types, a clean interface, and then implementing it, sometimes an interface doesn't really help much. And like in this example, right, you see the hose coming out, and then it looks like it's a nice fountain, but it's really just a stone with a pipe in it. Sometimes this separation and this rigid abstraction can also be harmful, and it's occasionally useful to break it open. And that's why I think it's so vital that you don't only know the abstract data types, and you know that there's implementations of binary search trees and all the like in programming libraries, so that you can use them. It's also vital for computer scientists to know what's inside the black box, so that in some cases you can break it open and exploit that fact and get to a better solution. With that, I want to see again a little bit how well these terms are known to you. Now, before I start that, let me double check that you can, that was the wrong one, this one, that you can actually answer with several questions, several answers. I'll wait a little bit to give few more people a chance to vote. It's a question with a lot of answers. I want to point you to a little nitpick here. Which of the following are examples of abstract data types? I wonder if I can... It doesn't want to zoom out. Okay, 30-ish people is what we had for the previous questions. So maybe I'll reveal the answers. So strictly speaking, I would say ADT is not an example of an abstract data type because it's just the abbreviation for abstract data types. It's not an example of it, but okay. Not so important. Let me show the answers. Stack is an abstract data type. We'll talk about that in a minute. Deck is a stack and a queue together, so you can use both ends. That's an abstract data type. Maybe not so well known, but occasionally used. Linked list is not an abstract data type, I would say. It's an implementation, so it's a data structure. And the same is true for binary search tree. Sometimes people use this a bit interchangeably with dictionaries, sorted dictionaries that will come below, but I would say it's a data structure. Queue is an abstract data type. Yeah, resizable array is a data structure. That's right. It's not an ADT. Same for heap. Priority queue is an ADT because there's, well, it is according to my definition. And symbol tables, again, that's the abstract data type that is implemented by binary search trees. So that's correct. Okay, cool. I hope we get the terms a little clearer or better separated in a minute. Let's talk about the simplest example maybe of an abstract data type, the stack. And as I said, an abstract data type has to specify the operations that you can do. And what's implicitly behind this is also what is a stack? A stack is a collection of objects. And you can do basically three things with it. You can ask, what is the currently topmost element on a stack? So you can return that item. And top is understood as not modifying the stack. You can push an item onto the stack. So there's a new book entering the stack, and you just put it on top, what we all do. That obviously grows the stack by one item. And you can pop the topmost item off. What you cannot do in a safe way is like take this book out and hope that the rest will not collapse. So a stack does not allow this. It only allows access to the topmost element. It's usually useful to also have a way to check if the stack is empty and to create a stack from scratch if you start with nothing. I guess that's known to you, but just to be on the safe side, let me ask you this little question to see if you understand that part and to make sure you're awake. So you have a stack with numbers, and in the picture I drew, it would be 1 is at the top. And again, I read the numbers top down. So this is top down, and you should do the same for the answer. This is top down, read the numbers on the stack. Okay, I see not everyone has voted, but the result is so clear that I would say you got this, and no need to waste more time on this. So obviously pop does pop, pop, and then you do one push of the 1, so you read this down as 1, 3, 4, 5. All right, that was easy enough. Now let's talk briefly about linked lists. There's different ways how you can implement a stack. It's an abstract data type, and it doesn't say how you implement it. But one typical way of doing it is like this, with a linked list. And for that, let me briefly repeat what a linked list looks like. I assume you have a programming language that allows you to generate objects. And these objects have fields, and one can be a value, and the other can be a pointer. And we will use this pointer. It's a singly linked list that I will create. It's a pointer to another element, so that will be just the next element in the list. So as an example, take the example from before. We had 1, which was at the top. And this has a pointer to a next element, and that was 3. So this points to the next element. And then we had 4 and 5. The beauty about linked lists is there's no requirement as to where these objects are really stored. They could be just arbitrarily scattered around in memory. And this will have a null pointer because it doesn't have a new element. Now that's a singly linked list. It has a beginning and it has an end, and we can traverse it by following the pointers. That's pretty much what a linked list can do. It's a very flexible way of representing a sequence, because at any point in time you can insert a new element by inserting a new element inside this pointer, if you like, pointing to the new element and from the new to the previous successor. How do you make a stack out of this? It's fairly simple. You just imagine that you have these boxes stacked on top of each other, and it always points to the next thing below it. And you have one global variable top that points to the topmost element. So you can access that topmost element through this global variable. And you can pop it by just setting top to the successor, and then this is essentially deleted. And you can add a new item by creating a new one here, setting its next pointer, and then rewiring the top pointer to point to this new element. That's how you do a stack based on a singly linked list in like 2 minutes. As most of you will have seen this, this is probably a sufficient level of detail. How good is this implementation? It's actually pretty good for a stack. It does all operations in constant time, and that's worst case constant time. So there's nothing else we could really hope for. And it requires a linear amount of space. To be a little more precise, we need n of these objects, each of which has to store well, the value that we're representing in the stack and a pointer. So we waste a bit of space in that we have n extra pointers. But other than that, the linked stack implementation is as good as we can hope for. Sometimes this requirement of having n extra pointers is too much, and we can think about if we can do away with these extra pointers. And well, yes, we can if we store the items in an array instead. Now, that again is also somewhat easy. We have an array, and I just draw it upwards to make it more look like the stack of books that we had before. And we stored the elements here. So we had 5, 4, 3, 1. And we have an additional variable top that tells me what is the index here. So it doesn't really matter where I start with 0, but let's say it's ordered like this. So top would store 3. So I would always know what is the topmost element. And I can push another element in by setting top to 4 and adding this new element, whatever it is. So far, so good. Easy enough. And well, you can do all the other operations. You can figure out how this works. The problem is, what do we do if we want to pop and the array is already used up? Because arrays need a fixed capacity. That's how arrays usually work. That's down to the memory management of operating systems and programming libraries. They allow you to allocate a certain chunk of memory, and that's it. You can't easily make it bigger than that if you need that later. So what you can do is you can either say, let's do a fixed size array and have a fixed capacity for our stack, and we can never ever go above that capacity. Then we need that capacity of space, but there's no extra pointers. This is really just the space for C elements. So that's good. In terms of space, this is efficient as long as C is close to the actual number of elements that we need. And all operations are at constant time again. So that's also great, except that this fixed capacity is a bit of a pain in some applications. If you don't know a good bound on the size, then you're screwed with this. So in the next little subsection, I want to talk about resizable arrays, a simple trick to get arrays that can, to the outside world, appear to change the size. Under the hood, they don't. It's an amortization trick, how you can create new space when you need it. I suppose many of you have seen this, so I'll go over this a bit more quickly. One little comment is you can see an array as an abstract data type where the operations are create me one of size n, and I can get and set certain cells at the index I. So of course, most programming languages have special syntax for specifying this because you use arrays all the time. But that's the usual way how arrays work. Now, I would still say an array is usually not seen as an abstract data type, but rather as a fixed specific data structure, because I don't know of a programming language that uses arrays for anything other than a contiguous piece of memory. But maybe it's sometimes useful to think about these operations specifically. That is what makes an array, really. Now, how can we do a stack of unbounded size with arrays of fixed size? We have to somehow allocate new arrays, obviously. And we can do this as follows. This was the invariance for maintaining a stack in an array. We have an array S, and it was drawn like this, right? You remember just a couple of slides back. And it had a certain capacity C. And we had a pointer to where is the stack currently. So point top would essentially store the index of the topmost used element. Now the new thing is that we insist that at any point in time, this capacity is sandwiching the number of elements in this way. N must be at most the capacity, well, we have to store the elements. And we also want that the capacity is not 4 times bigger than n. So we don't want an overly large array if there's not also many elements. If we can maintain this invariant at any point in time, it means we can always add more elements because the capacity grows with the number of elements. But what I haven't told you so far is how we can maintain this invariant. And the a conventional easy way to do it is as follows. Before we push a new element, we check if we've reached the current capacity. And if so, we allocate a new array of twice the size of the current size, and we copy over all elements. So that was the current capacity C. Now we double it, and we make sure that this lower part is copied over from here. That's quite expensive, but we'll see that it pays off in that whenever we have this expensive operations, there's many cheap operations after that. The same thing if we remove an element and that brings us below our capacity bound, we do the very same thing, interestingly. We allocate a new array of twice the size of the current stack and copy all elements. And that's it. It's simple to implement and program, but I want to make sure that you understand what this is about. So let's do this little question. Which of the following statements is true about a resizable array when it currently stores n elements? And again, read very, very carefully. There's nitpicks in the formulation. What I mean by nitpicks is pick the statements that are always true. Not those that sound just reasonable, but those that are really clearly true. In a sense, this question is my way to see, have they seen resizing arrays? Yes, but have they seen it and totally internalized it? That's what this question gets at. And from a theoretical perspective, if you like. Okay, I think most people have voted. So let's see what you came up with. And I'll show you my answer. And want to briefly tell you a little bit about why I think the others are not as true as I would like them for this question. Oops, that was not what I wanted. Okay, I didn't want to reveal the answer right here before we do the analysis, but because most people have seen this, maybe I'll do this anyway. I think this is the correct statement, and I'll justify the statement for you in a minute. The first statement is not really true because the number of elements that are currently stored that might fluctuate up and down, and it's not always exactly 2n. Nitpick, as I said. Adding and deleting an element at the end takes constant time. So here the nitpick is, if I say constant time, this means worst case constant time. If there's no other qualifier, you have to assume it's worst case. And that's not true, because in a resizable array, if we have to resize, it's expensive, takes linear time, as we'll discuss. And the last point is, inserting and deleting any element takes order 1 amortized time. If this was combined with the second answer, it would be true. The last element can be deleted in amortized constant time. I cannot take out any element in the entire array. I would have to shift the rest over. Okay, that was maybe a bit of a mean question, but I wanted to see if you can follow along with this. But let's briefly do this amortized analysis of the resizing arrays, because amortized analysis will come up later in the class in a more complicated setting So it's useful to get this sorted once and for all here in this simple setup that is probably familiar to you guys. Okay, what is amortized analysis about? It's a common term in algorithms and data structures, so definitely you should be able to recognize what it means. It's the concept that any individual operation in our sense of the array implemented with in the stack implemented with resizable arrays. Any individual execution of push and pop can be very expensive if we have to copy the elements to the new array at precisely that time. But the observation is, because we always double the array right away, we create enough empty space so that one expensive operation pays for a lot of the future operations to be cheap. So that if you average them out, each is cheap on average. That's what amortization means. And in our case, we have there's a widely used, there's different proof techniques and templates that you can use to prove amortized bounds. I will focus on the one that I find most versatile. It's maybe not the most intuitive one, but it's the one that that works for all the problems that we will encounter. So I want to introduce the general version here right away. And the idea is we define a potential function. And that's some magic definition that you have to come up with. This is reminiscent a little bit about the loop invariant. You have a proof template that's fairly simple, but you have a creative step where you have to understand the problem to see what you have to fill in for this step. That was the loop invariant, and here it's the potential function. Okay, let's look at what the proof template works like. It defines an amortized cost for an operation, which is the actual cost, and in this case, -2 times the change in this potential. And this 2 is a constant that you usually work out after the fact. When you've done the analysis, you find that 2 is the right constant in this case, and so that's what you use. For other applications, it might be that you need a different constant. Okay, but that's a definition. Now let's look at what happens with push and pop. If we have a cheap operation, that means there is space in the array. The actual cost is just one array access. So by cost here, we count the number of array accesses. That is, again, a quick comment from the off. We used to talk in the previous unit, we talked about elementary operations, the dominating operations for a certain task. And here, for this simple application of a resizing array, how often do I access, read, or write a cell in the array? That's what we pick as an elementary operation. So our cost is the number of these array accesses. A cheap push and pop has exactly one of these array accesses. That's the actual cost. But the amortized cost has to add the change in potential. And here, if you look at this potential, now I should give you a little bit of an intuition. There's the bounds of 1/4 C and C. And n can be anywhere in this range. So n could be here. And n can move up and down via push and pops. So it can wiggle around here. And what this potential function does, the phi, is just the distance to the closest boundary. And in this case, we're getting closer to the lower bound. So in this case, phi is this distance. If n moves further up, it becomes this distance. Now, if you do a cheap push or pop, that means you move around with 1 inside this range. You're not at the boundary. So you go from here either to here or to here. If you go away from the boundary, you actually gain a credit. But we can't really use that because what we have to say here about the amortized cost has to be true in every case. If you move closer to the boundary, you lose 1 credit, by which I mean you lose 1 in phi. And because we double that, the amortized cost is 3 of such an operation. It's at most 3. It can be 1 if you really move away from the boundary. But that's the worst case. If you have one of these expensive operations, say a push, so that's the situation where your n reached the capacity and you have to double the array, then you have to copy the n elements from the previous array to the new. So that means n times you read and n times you write an array cell, plus the new element that you add in. So that's the 2n plus 1 array accesses for the expensive push. But it creates n credits in the potential function. Well, I would say that's actually n minus 1, right? If we're strict. So the amortized cost is 2. I think I just forgot that we also add 1 element at the same time. It might be the same here. If you add those 2 up, you multiply this by 2, and you add those 2 up, then you have the 2n cancels with that 2n, and then it's plus 1 minus 2. It's actually 3, is that right? Let's do the calculation in slow-mo to not screw it up. No, I was right. It's more expensive and it's 3 because I didn't double this. So that's the 2n cancels, and here we have the minus. All right, so it works out to 3. If you have the copying pop, that's similar, but now you reach the lower range of your capacity. Then again, you have to copy elements. And I think I screwed this one up badly. I think you also have 2n plus 1 copies because n is the current size. And but you only get half n credits. So this is the case where you notice that your constant here was not big enough. We have to change this to 4. Otherwise, this doesn't work out. We need that the factor here is big enough to cancel the actual cost. Now, if we add the 4 here, that will change the amortized cost of these operations, but it will only increase the constant. So this goes up to 5. And here again, we have the 4 plus 1, so that goes up to 5. And then similarly here, but let's do it in slow-mo again. Minus 4 times the 1/2 n minus 1. So those cancel, and then we have 1 plus 4. So this is also 5. Sorry for that confusion. I should have caught that mistake earlier. I'll fix the slides, but I think it was also insightful for you to see how these proofs are usually constructed. You start out with a constant here and see if it was big enough. And if not, you make it a little bigger. And usually either it works then, or you keep increasing the constant, which means your proof is flawed and something's wrong. Okay, let's I'll erase the side calculations. We have shown that in each of the cases, we have an amortized cost of 5. Now, what does that mean for a sequence of m operations? The total cost of that is at most this. So this is something I want to show. If we say AI is the amortized cost for the ith operation, so that's the actual cost plus the change in the potential. In our case, we say it's -4, and then the new potential minus the old potential. So by this phi I just mean the potential after step I. Now we want a bound on the total actual cost. But what we have is that our amortized cost is at most 5 for all the operations. So what we can say is if we sum up the amortized costs for for a sequence of m operations, that's at most 5m. But we also know that this sum is telescoping in the sense that if you insert the definition, you get the sum over all the CI's. And then we have -4 and then this sum where, well, let me write it down, but you can probably see this. In this sum, there's always one term that cancels the contribution from the. So the only thing that remains from this is the total actual cost. And then we have -4, and what remains from this sum? What's not cancelled is the last term, the phi m. And we have a minus phi 0 at the beginning, the initial potential. And all the other terms in the middle cancel. And now we have a nice inequality where you can solve for the total cost of the total actual cost. And you just bring this to the other side. So the total actual cost is the sum of the amortized costs. That's 5m. And then we have to add the 4 phi m and subtract the 4 phi 0. But we can drop the. This is always just making it smaller, so we can, as an upper bound, do the 4 phi m. And so here, another little mistake. We get a bound, the total cost, that's the total cost, sum of the CI, is at most the total amortized cost, which is 5 times m, plus the final credits, that's phi m. Now, let's see how we can fix that part. The total amortized cost was 5m. And okay, I switched between n and m. Let's keep it with n. Okay, let's m operations. So I should have written m here all the way. How big can the final credits be? The phi is always at most half n. So that part's correct, but we increased that constant to 4. And sorry, this was a lot of corrections. Plus 2n. Okay, that was a lot of work, but finally we've shown this bound, and that of course is theta of n plus m, which is the result we claimed here. So to wrap this up, if you have a resizing array and any number of operations m and a final size n, the total cost will be bounded in this way. The total cost is n plus m. And if you start with an empty array, the final size will never be bigger than m. So it's linear in the number of operations, which means each individual operation on average can only cost a constant time. That was amortized analysis of resizing arrays. That's probably a good point to check if you have any questions about this part. Again, I apologize for the confusion on the slides. Well, if questions arise later, we can address them then. If not, I'd like to conclude this part with queues, which are like the sister of stacks. They're like if you have to queue for getting into some shop, you can in-queue at the end, hopefully only there, if it's a fair queue, and dequeue at the front. So you add new people here, that's in-queue, and you dequeue at the front by taking the first person off and allowing them into the store. Implementation-wise, it's exactly the same as for stacks. You can use linked lists and you can use arrays. You have to be a little bit more careful because of the two ends, but it's not really a big difference. For a fixed size array, you have to deal with the wraparound in the queue, but you might have seen this before, and if not, it's not relevant for our class. And a final abstract data type that I want to mention is that of a bag. And it comes from the question, what do stacks and queues have in common? They're essentially special cases of just a collection. So this is also the Java name. It's roughly the same as a bag. A collection is just anything you can put items in and you can get items out. And I called this here delete any because you don't really have control over which item you get. You just remove any of the items in the bag. It's sometimes useful. It's not that you can implement a bag more efficiently than a stack or a queue. It's just sometimes useful to specify, I don't care about the order, use whatever is convenient for you. And yeah, that concludes the part of the very elementary basic data structures. Explicitly, I made this a bit longer than necessary because of the amortized analysis that we will reuse for different algorithms. I figure it's good to leave you 1 or 2 minutes of a break before we jump to the next topic. So let's say we continue at 11:57. It doesn't have to be a nice little round time. Put that nice in the middle. Okay, see you in 3 minutes. right, welcome back. It's 11:57 on my clock, so time to continue. And time to leave the simple elementary data structures and jump to something slightly more interesting. In the next subsection, I want to talk about priority queues, one of the building blocks for many algorithms and data structures, and you will see some examples later in this class as well. So I want to briefly cover these. Also, it was one of the topics that was were half or less than you have seen it before. I want to start off with a little question just to see again how well exactly you know these things. There you go. But I don't really want to wait for your answers at the moment. So the question is about heap ordered trees. This is different from priority queues. The priority queue is really the abstract data type. And I put here this, whatever it is, gin and tonic in the plane. You can sometimes have people with different priorities. You can have business class, first class passengers. And if you're traveling and waiting for boarding at the airport, it might happen that there's not the standard queue where everyone just enters at the end, but some people are allowed to jump the queue and have priority boarding. So this is that explains the picture, just to keep that memorable for you maybe. The priority queue abstract data type is a bag where the items have priorities. And that influences the order in which they are retrieved from the bag. But to be a little more specific, I listed the operations here because we will need some of these for the tutorials as well. We can construct a priority queue from a given number of elements. If they're stored in an array, that's the most convenient way. And you can also start with an empty priority queue and then insert elements with a certain priority. The difference is that the construction from a given set of elements might be cheaper because you can do a bulk insert instead of inserting them one at a time. And we'll see that precisely this happens for binary heaps. Then there's an operation max, like top in the stack. That is just retrieving the item that would be deleted next. So that's the item with the largest priority. And you can delete the maximum, which removes it and also returns it. Sometimes you also need an operation to change a key or to delete an element with a pointer. Well, I won't obsess about this too much. I just want to mention, for those of you who have seen it before, you usually assume that the element whose key you're changing is given to you by a pointer into the data structure. So you somehow keep track of where this is, and you can jump right to that element. As something that's sometimes not stressed too much in theory classes, but if you implement binary search, binary heaps, and try to do the change key, you need to know where the element is. Maybe this will make more sense in 20 minutes. And we can sometimes do a check for empty, but that's easy. So priority queues turn out to be a fundamental building block for graph algorithms, for coding algorithms that we'll see, and they often simplify how you can specify an algorithm. So they are really fundamental and widely used. Now, a priority queue is really not one ADT, but two, because I specified here everything for maximum, but sometimes it's more convenient to have the minimum instead of max. So same game, it's just flipping everything around. The theoretician would say, wow, you just invert the order. Whenever you have two elements, you define the order that gives exactly the opposite answer. And that's fine, but in practice, you sometimes just want to not confuse the user by using the exact opposite terminology. So both exist, and to make it a little confusing for students, some textbooks use the min-oriented version, some the max one. I used the one max oriented will be what we use in this unit, because that's what the videos I mentioned on the website also use. So to be consistent with those. All right, I haven't started the other question, so let's first go to that one. And well, we'll do that differently this time. I will just stop the question now. I'll show you the results. But we will come back to this later. So instead, I want to ask this question. If we start with an empty priority queue and insert these numbers and then do a delete min, what happens? I guess you guys were still busy with reading the binary heap answers because they were long and lots of text. Okay, now the answers come along. And to make it a little more challenging, notice I used delete min here. So this is the min-oriented version. Despite what I said, in this unit, we want to use the delete min. This question, the delete max, this question uses the delete min. That was not supposed to be a trick question. Probably should have changed it to delete max, but let's keep it as it is for now. Okay. Yeah, most of you got that right. I got a few people confused with delete max, I think. Of course, it's 1 if this is the natural order. If you insert these elements into the priority queue, delete min will remove the smallest of those and return it, and that's the 1. That's why that's the answer. So that was that. And let's now look at how we can implement priority queues. First of all, we can do very elementary things. We can keep an unordered list of items. Then it's cheap to insert, but for delete max, we have to scan the entire list. Not very interesting. The opposite is we can keep a sorted list. Then we can easily delete the max because it's always at one end. Say you sorted decreasing. So well, this is confusing. Decreasing like that, I'm mirrored. So you have the smallest element at the beginning. But insertion can take linear time because you have to move elements around. I'm assuming it's well, if it's an array, you have to move elements. If it's a linked list, you have to find the insertion position, and you can only do this by walking through the list. So both of these are not really good. But they might be inspiration for looking at the better solutions. The problem here was we went to two extremes, either not sorted at all or completely sorted. Not sorted at all was good for insert, completely sorted was good for delete max. Maybe we want to do something in the middle, slightly sorted. So what's a slightly sorted list? A slightly sorted list is a binary heap. In a way, that's one way to see it. And there's really no good. There's really two ways how you can define a heap. A more intuitive one is the tree view that I will mostly use. But for implementations, there's an array view, which is also useful. Let's look at the tree view first. And that comes back to the question I posed at the beginning. A heap is a tree where the shape is restricted to a complete binary tree, and I will usually draw these like this. The reason for that is a complete binary tree means it has full levels, except for maybe the last level. Now this is a bit, this one should be a little closer to that, so that's a left child. That's a complete binary tree. So a heap, in our setting, a binary heap has to have this shape. It's a binary tree, but it has to have this very specific shape. All levels full, and the last level as far to the left as possible. And heap ordered, which means that the keys, whenever I compare two keys, and one is the father of the other, the parent of the other, I should really use the gender neutral version here. Doesn't matter. So if the parent has a key and the child has a key, then the parent key must be bigger. We can store such a key, store such a tree conveniently in an array because it has this very specific shape. And what you do for that is you essentially walk through the tree in this way, level by level. So sometimes called level order traversal. And then you assign indices in the array like so. You start with 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on if the tree was bigger. And then it turns out that magically, if you do that, the array represents a valid heap if and only if for every index we have this condition that the value at this index is smaller, is at most the value of the index where you take I divided by 2 and round down. I suppose you have seen either one of these two conditions, and maybe even both. Both are equivalent in terms of defining things. Usually array view, again, as I said, is for implementing, and the tree view is to make sense of what's happening. So I want to show a concrete example, just so that we're on the same page, what I mean with the heap order. And so here's just a specific example that I made up. And so a few more. And as you can see, it has the shape that I drew before. It's always of this almost complete binary tree. And whenever we follow a path down, say we go like this one, then we always have this is less, that's a bit too fat. This is less, okay, I'm drawing this on like that. Whenever you follow a path from the root down, or wherever you started the tree, if you follow a path downwards in the tree, the keys only get smaller. All right. Let me take a copy of this with me for later, because I will need to draw such trees again. Why do we like exactly this shape? I want to motivate this a little bit before we move on. You will also, I mean, the other answer, one answer to this question would be, that's how it is, and that's how it works. But there's a better answer to that. And I have a couple of reasons here to motivate it a bit. One is, there's only one possible tree shape, and that makes life simple. Also, complete binary trees have minimal height among all binary trees, because you put nodes as high up in the tree as possible. So you fill them up in the top part of the tree as long as that's possible, so that they will have minimal height. And we'll see that the operations are essentially bounded by the height of the tree. And last, by fixing this specific shape, we have a very simple formula for embedding nodes in an array. Remember, this level order traversal was giving rise to this very nice formula for the heap property. And similarly, you can navigate from a node to its parent. That's what we used in that formula. You can navigate to the parent by going to the number divided by 2 rounded down. And you can also go in the opposite direction. And why do we like, see if I can get out of the way here a bit. Why do we like heap ordered? Well, first, the maximum is always at the root. So the maximum function is trivial to implement. And also, it's sorted along the paths of the tree, but leaves a lot of flexibility in how to assign keys, how to mix the paths in this tree. So it's only very slightly sorted, really, and that will be useful in maintaining this in operations. Okay, so let me just reveal the answers to this old question. No, that was not the one. Sorry, this is the one. So you can see this on the site now, and I like to ask this question precisely because, as you can see, a couple of people mixed it up with the second answer. And that's a typical confusion because the two concepts are so similar. It's often that people confuse it with binary search tree properties. We'll come to that. But this is really what heaps are about. Okay. In the remaining time, I want to sketch how you can do operations on binary heaps. So for that, I'll use my little example heap here. Make it a little smaller, and maybe we can get rid of the blue part, which we don't really need. Okay, that takes too long. All right. So here's our binary heap. How can we insert a new element? Say we want to insert the number. What's a nice example? 68, say. Because of the shape, don't want to write this in red. The shape means there's only really one possible position for this new key to go. And that's right here. So we can only really put the 68 here, which means it would connect to this tree like that. Because any other position would violate the shape constraint. So we would rewire this like that. And now we have a problem with the heap property. Because the heap order is violated, potentially, and in this case it is, because 68 is bigger. So what can we do? Well, we take this thing and we modify it. I think I need to make it a little smaller. I hope it's still big enough for you to see. So that was the initial state. Now, we can't really leave it in that state because the heap order is violated here. So we have this problem here. So what we do is we flip those two numbers. Now, I don't know, somehow the gray thing that I drew here nicely is lost. Would have liked this to be like this. Never mind. So we swap those two keys. And try that thereby to repair the heap property. So we let this item 68 swim up the heap. So at this point, we're a little better. This is fine, but here the violation still exists. So we have to continue and do this one more time. One more copy of the tree. And swap those two. So we have 68 here. And the 66 from before. And now this is also fine, and this is fine. So at that point, we have reestablished the heap variant, and we're good. This is a valid heap again, and we've inserted this new item. One thing that is important at this stage is, let's see if I can squeeze myself here. While you do this, you swap a larger number up. So this was fine before, and it's also fine afterwards. Whenever you do this, the other children of affected nodes, they're never they will never violate the heap property. So this is never an issue. That was insert. As always, if you have questions, shoot them up. So maybe this is a good time to discuss them. Let me stop the poll now so we can see the questions. Let's see if I made a mistake for the first question. Where am I? Pop this. Yeah, 85 is a 55. I miscopied from my sheet. Thanks for pointing that out. Good, I copied the wrong version 500 times. But no, for the record, let's also fix it up here. And let's copy that one again, even though it means I have to delete the blue part again. Yeah, thanks for pointing that out. For priority queues, would you often plot a graph with items on the x-axis and priorities on the y-axis? I'm not sure what the question hints at. You can do this. It's sometimes insightful. The problem is x might not be a number. It might not be comparable. So the priorities have to be ordered so that you can talk about what is a large priority, what's a small one. The items that we insert in X, they need not be comparable, so sometimes you cannot draw them on the axis. But we will occasionally use that, maybe. Are you saying that the leaf is smaller than the parent? Yes, that's what I'm saying, except that leaf is a special case. Maybe this was the mistake from the slides. Any child is smaller than its parent. That's what I'm saying for the heap property. All right, that was insert. If you have questions to insert, put them in the Q&A. Then the second operation that we want to look at is how to delete the maximum. I promised to stay consistent to the book, so this will be delete maximum, not delete minimum. Let's get my favorite tree here again. Good that I changed this, and let's move these away. And keep hold of it. Now we want to make this smaller, a bit smaller again. Now, deletion of the maximum element. We want to get rid of the biggest element. Finding it is very easy. Of course, the max has to be at the root, so it's right here. And returning that would be easy. The problem now is that we want to delete it. So we store 86 to return it. And now we want to vacate this cell. So we want to get rid of the 87. Now, of course, that's not a good state to be in, because now we don't really have a valid heap. So again, we have to do something. But let me write this down. Finding the max is easy. But when we remove it, we are no longer a complete binary tree. So we have to do something about this. And the only thing we can really do is change the shape of the tree again in the only way that's allowed. And that means taking out this element and moving it up into this gap. So that's what we'll do. The 25 moves up here. This becomes empty, and this is gone. So we're almost good. The heap shape, the tree shape is fine. But the heap property, the heap order, is violated. So we have to do something about this. We have to fix it again. And how do we do this? Well, there's only really one thing we can do. We have to let this element sink down to find a proper place in the heap. That's the term that's usually used. Now, probably need a little more space. So how can we do this? Let's take our favorite tree again. The problem here is that we have two violations. It's violated here and here, but we can only put the 25 down into one of the two slots. Now, which one should we take? If we would swap the 25 with the 66 would still violate the heap condition with the 70, so we can't do this. Instead, we have to compare these two children with each other, and we take the bigger one. So that's the bigger child, so that's the one that we swap. So let's actually do this. Maybe we don't need the red circle anymore here. We put the 70 up here, and we put the 25 down there. Now, by picking the larger child, we make sure that this is fine, and so the whole subtree here is fine. And we made sure this is fine, but we still have a violation here. So we do another round of swapping. And so that you can follow this in the lecture notes, I'll just keep that here. So we swap those two again. Used blue for the swap. So that's the bigger child in this case. So we take that one, swap it with this one, and then you're left with 55 and the 25. And now we have restored the heap property. And that's how you delete the maximum in a heap. Again, any questions, let me know. I know I'm pacing fairly fast through this, but I think if you understand this on the example, you should be able to figure out how this works in general and be able to implement it if necessary. Yeah, as I said, the videos show this in much more detail, and the textbook also has code for this. The last operation I want to discuss is how to construct a heap when we start with a given set of elements. And Well, we could do n times insert. But you would, if you analyze this, the total time would be n log n overall time. You have to be a little careful because the insertion takes time log of k for the current size of the heap, and the heap initially is small. But if you look at the last half of the elements, then the heap has already size at least n half, and that's enough to establish the n log n. But we can do better than the n log n. And the idea is to start with small heaps and merge them. So you first start, let's take our, I probably don't have time to go through the full worked example. So you take the last half of your elements and put them as individual numbers here. Then you take the next quarter of your elements and put them above these. Sorry, that's this should be here. And you make these little heaps of size 3. What you have to do for that is let each of these sink down. All right, after you've done that, you have these little heaps. And each of these is a nice little heap. Let me indicate that with the outline. So what I mean by that, each is a true heap in that it has the right shape and it satisfies the heap order. Now you put the next elements up here and do the same thing. You connect these two heaps, pair them up, and again you do a sink for the root. And you do this one more time, and then you have the entire heap. And now, why is this more efficient? You need roughly a quarter times sink in a heap of size 3. At the next step, you would need, for an eighth of the node, sink in a heap of size 7, and so on. This is always a power of 2 minus 1 at most. The last one could be smaller. And here you divide by n to the 2 to the k. Now, if you sum this all up, you will stop when k is log n. And so summing these all up, because most of the insertions of elements are in small heaps, the total cost is linear for this heap construction if you do this bottom-up merging of heaps together. So let me just write that down. And that only leaves to wrap up the binary heaps. I will prepare that for next time, so that we save a little time on that. Sorry, you couldn't see that last part. That concludes the construction of heaps, and that concludes the 3 basic operations of a priority queue and how you can do them on binary heaps. You can similarly do the change key operations by letting a node sync up and down depending on how the node, depending on how the weight has changed. And you can do similarly the other operations. But what I've shown you gives you the core picture. and that's how we use that. I'll give the overview slides next time to save time on that. Thanks for showing up. Thanks for coming around. We'll meet again next Tuesday at 11 a.m. Same slot as always, same link as always. Don't forget the tutorials for today. The tutorial 1 problems are online or have been online since last week. If you haven't looked at those, definitely do that before you go to the 4 p.m. tutorial slot today. Take a piece of paper with you and try to solve them before you get the solutions presented. That helps you much more than just sitting in and listening. If anything is unclear, please use CampusWire for questions and the chat rooms. And with that, see you next week. Have a good rest of your week and hope you enjoy the tutorials. Bye for now.